In this lesson, we're going to talk a little bit about the conceptual ideas behind limits and a lot about the practical interpretation and use of limits. So let's just jump right in. When we write an expression like is displayed here, we're basically asking a question, and the question is, in this particular case, what is happening to the values of that expression, in this case x squared plus 1, as x gets closer and closer to the value of 1? What happens to the expression's value as x's value gets close to, in this case, 1? Before we get into the interpretation, let's actually talk about how to handle the notation itself. The expression, the LIM, stands for the word limit. So if you were reading it, you'd just say limit. The expression underneath the LIM is read x approaches, and in this case 1. The right arrow is read as approaching. In this case, there's an x there, so x approaches 1. So if I were to read that whole expression, I would say something like the limit of x squared plus 1 as x approaches 1. So it's the limit of whatever the expression is as x approaches whatever the value happens to be, in this case a 1. What you need to keep in mind, though, is that with limits, we're not particularly concerned with the value at the number x is approaching. The idea of a limit is we're looking at what happens as x gets closer and closer and closer and closer to the value. Like if you're taking a trip, you're not particularly worried about what you're going to do at the destination. You're concerned with what's happening as you get closer and closer to the destination. That's sort of the idea of a limit. You're getting closer and closer to something. You're not really so concerned about what happens at the value, but what happens as you get close to that value. Just keep that in the back of your mind as you go through these limit problems. Now, even though we're only interested in what happens as you get closer and closer to 1, if you think about it, looking at it from a number line perspective, there are still two directions from which you can approach 1. If you put 1 on a number line, you can be coming and getting closer and closer and closer to 1 from the left, or you can be getting closer and closer to 1 approaching from the right. When you're approaching closer and closer from the left, we call that a left-hand limit. And when you're approaching closer and closer from the right, we call that a right-hand limit. Mathematicians love notation, so what we're going to do is create a notation for a left-hand limit and a right-hand limit. For a left-hand limit, we will take a minus sign and make it a superscript to the value that x is approaching, in this case a 1. And we're interested in a right-hand limit. When we're approaching from the right, we'll use a plus sign as a superscript to the value that x is approaching. And again, in this case, it's a 1. So they're not plus 1s and minus 1s. They're from the left, from the right. A minus superscript means you're coming from the left, and a plus superscript means you're coming from the right. So a minus is associated with the left-hand limit, and a plus is associated with the right-hand limit when they're written as superscripts to the value that x is approaching. Once you get used to it, it's simple enough. Let's take them one at a time. First, let's focus on the left-hand limit. What happens to the value, in this case x squared plus 1, as x approaches 1 coming from the left of 1? On a number line, you can sort of visualize this, and so I just started close to 1 at 0.9, and I kept getting closer and closer by adding a 9. So we start out at 0.9, then we get a little bit closer by going to 0.99, and a little bit closer by getting to 0.999, and we could keep adding 9s, and we would get closer and closer and closer to 1 without ever actually reaching 1. That's the idea of approaching 1. Let's actually table that and calculate some values. This is a good time to get used to your calculator. Remember, you can only use the Casio FX260 solar calculator. Go ahead and get it. It doesn't cost very much. practice with that one. There's no sense in learning how to do something with a different calculator when you can't use it on your test. So in any case, what I want to do here is I want to just start off with the 0.9, and I want to plug that in to the expression that we're using and see what happens. If I take 0.9 and plug it in and square it and add 1 to it, and again, practice this in your calculator, you'll find out you get 1.810. Then we get a bit closer, 0.99, plug that in, square it, add 1 to it, and you'll find out you'll get 1.9801. Keep it up, do 0.999, square it, add 1 to it, and you'll find that you get 1.9988001. You could actually do it again for 0.9999 if you wanted to, but you sort of get the idea. And if you look at the progression of calculated values, it seems that they're getting closer and closer to 2. So as x gets closer and closer and closer to 1, x squared plus 1 seemingly is getting closer and closer and closer to 2. And that's the sense in which we say that the limit of x squared plus 1 as x approaches 1 from the left is equal to 2. Let's move to the right-hand limit and do the same thing. This time we're approaching 1 from the right. I'm going to look at it from a number line perspective again. So I'm going to take values closer and closer and closer to 1, but this time coming from the right. So I'm going to start off with 1.1 and then do 1.01 and then 1.001. I could just keep adding zeros in there, 1.0001 as long as I wanted to, and I would be approaching 1 from the right, but never reaching 1. That's the idea of the limit. So let's table those values and do exactly the same thing. Start with this 1.1 and plug it into the expression, which means we need to square it and add 1 to it. Well, if you square 1 and add 1 to it, you'll get 2.21. Moving closer, plug in 1.01, square it, add 1 to it, you'll get 2.0201. Getting even closer, 1.001, square it, add 1 to it, you'll get 2.002. And if you wanted to do 1.0001, you could, but what you would find is that you're getting closer and closer to the value of 2 as x gets closer and closer to the value of 1 from the right. And in that sense, we would say that the limit of x squared plus 1 as x approaches 1 from the right is equal to 2. I used particular numbers, so for at least for a minute, I want to take the particular numbers out and write this result in general. So instead of saying approaching 1 and approaching 1 from the left or from the right, I'm just going to say approaches a value c, and that the function is not necessarily x squared plus 1, it's just some general function f of x. So I can write this without any particular values, and there's some benefit to having to see this written out without a particular example in mind. So all I did is take out the particular numbers. If they're both the same, there's really no need to distinguish between them. So what we typically do is if the left-hand limit and the right-hand limit both come out to be the same thing, we just drop the superscript minus and plus and just call it the limit. We drifted away from that particular example just a minute to generalize the result, but let's go back now to that original example. We found out that the left-hand limit was 2 and the right-hand limit was 2. So according to what I just said, we can just get rid of the plus and minus and just say that the limit of x squared plus 1 as x approaches 1 is 2. Since the plus and the minus come out the same, there's no need to distinguish, and you can just drop the superscripts and just write the limit without them. But that limit only exists if the left and right-hand limits are equal to each other. It might be beneficial to look at what's going on graphically when you're doing this. I did it with tables and I didn't really look at a graph, but it's probably helpful to see what's going on graphically. That function f of x equal x squared plus 1, if you graph it, it's just a parabola. Here it is. So what's going on graphically when we're taking these limits? Just think about it. From the left, we're looking at what's happening to the y value. Remember, y is f of x, and it's just x squared plus 1, so that's a y value. We're looking at what's happening to the y value of a point that's moving along the curve from the left, because it's a left-hand limit as you go toward 1, but from the left. So think about it this way. If you're headed toward 1, an x value of 1, you're a point traveling along that curve. So if you get close to 1 from the left, just say you're sitting at that curve where that red dot is, and you're getting a y value. But then you're getting closer. You get even closer, you get a different y value. You get even closer, you get a different y value. You get even closer and you get a different y value. And you sort of see graphically the same thing that we saw before. It looks as if that y value is getting closer and closer to 2. As x gets closer to 1 from the left, the point traveling along that curve is getting closer and closer to a y value of 2. And notice that's just what we got earlier without looking at the graph. So the graph is sort of a visual confirmation of what we did strictly algebraically before. And you can do the same thing from the right. If you're looking at a right-hand limit, you're coming in toward 1, but you're traveling along the curve from the right side, headed toward that value. So if you start at a point relatively close to the value at 1, you get a y value. But then if you get a little bit closer, you get another y value. If you get a little bit closer, you get yet another y value. If you get even closer, you get another y value. And the same thing's happening again. It seems that the y values are all getting closer and closer to 2, which again is exactly what we got earlier. So this is just a graphical, a visual way of talking about what we did completely algebraically earlier. And that's a useful thing to have two different ways of thinking about this. In any case, those are what we mean by left and right-hand limits. And when the left and right-hand limits happen to equal each other, we just drop the superscripts and say the limit itself is that value. This sort of summarizes where we stand up to this point. The limit of f of x as x approaches c from the left is a left-hand limit. The limit of f of x as x approaches c from the right is a right-hand limit. And if those two values are equal to each other, you just drop the superscripts and say the limit of f of x as x approaches c is whatever that common answer came out to be for the left and right-hand limits. And if they aren't the same, you just say the limit does not exist. I'm going to highlight this again later in a summary context, but it's worth noting probably at this point that when you're dealing with polynomials, things are really easy. A polynomial function is a sum and or difference of numbers times x's to positive powers strung together with pluses and minuses, and there could be a constant on the end. It's just the polynomial functions that you've been dealing with for years. But if that function is polynomial, the left and right-hand limits are always going to be equal to each other. And all you have to do to find them is to plug the value that x is approaching into the function. It's going to be the left and right-hand limit every time. And since that's the case, the left and right-hand limits will be equal to each other. And since that's the case, we can just drop the superscripts and just say the limit itself is what you get by just plugging the value x approaches into the function. That works for polynomial functions every time. So you don't have to go through so much work to get the answers if you're dealing with polynomial functions. So the moral of the story is you should hope to have all polynomial functions in your limits. Of course you won't, but the more the better because they're easy. As an example, what if you had the limit of the expression 4x cubed minus x squared plus 1 as x approaches 2? Well, what I just said is if it's a polynomial, you don't have to go through all this left and right hand stuff. It will always be whatever you get by just plugging the value that x approaches into the expression. So all you have to do is take the 2, plug it in for x, cube it, multiply it by 4, then square it, do the subtraction, then add 1, and when you simplify, you get an answer of 29. That's all you have to do. So when you're dealing with limits involving polynomial functions, life is good. You just plug the value that x approaches in, and you have your answer. What you're going to find out as you work through the problems in this assignment is that a lot of the discussion in introducing this material is to handle the special cases that require extra thought. When you actually do a lot of the problems on the assignment, you're going to find out that what you have to do is plug things in and calculate, and that for a lot of the problems, you don't have to really think too much about the theory. And so I want to get you used to the fact that there are only a few of these problems where you have to really rely too heavily on the ideas that we've talked about, spent so much time talking about, and that in fact, a lot of the time, you'll just be plugging values in. For example, if I ask you to find the limit of this rational expression, x squared minus 2 over x minus 1, it's not polynomial, so there's nothing that we've said so far that guarantees that you can just plug it in. But as a matter of fact, you can, and get an answer of 7. And in general, for a great many of these problems that we'll be doing, if you can just take the value that x is approaching and plug it in and get an answer, that will be the answer to the problem. So that's the nice thing about this section. Huge number of these problems will be like that. Just plug and get an answer and you're done. Look at this one. Again, it's not polynomial. However, if you plug 3 in for x and do the calculation, you'll end up with the square root of 2 over 8. That's your answer. Here's another one. But what happens when you try to plug in here? You get 0 over 0. That's an indeterminate form. That flags something in your mind that says we've got a problem here. But it turns out the problem is fairly easy to solve. When you see this 0 over 0, when you're trying to just plug in and get an answer, it's trying to tell you something. Whenever you get that 0 over 0, that indeterminate form, when you're evaluating a limit, it's giving you a clue that that expression will actually simplify. And if you go back and simplify it first, you'll be able to plug in later. So you'll still be able to plug in and get an answer, but it requires a little bit more work. So when you see that 0 over 0, you don't give up, you simply back up. Back up to the beginning. And the trick in this case is noticing that the numerator is the difference of two squares. X squared minus 1 factors into x plus 1 times x minus 1. And at this point, you probably see what's going to happen. The x plus 1 is just there, but the x minus 1 in the numerator and the x minus 1 in the denominator are going to cancel. And when you simplify, that just leaves you with an x plus 1. And at this point, you can plug 1 in and get the answer. So you're still able to just plug in and get an answer, but when you see that 0 over 0, it's flagging, and a lot of times it's telling you need to go back and factor and cancel. You'll see another problem where it signals something else, but most of the time it's going to be a factor and cancel type thing. So as a matter of fact, most of these limit problems are fairly straightforward once you start practicing and working a few. Now how about this one? If you actually did the algebra preliminary video and the work there that as I suggested at the beginning of the course, you've actually seen that expression, not the limit part of it, but just the expression. I actually worked that problem on that video. And the trick from that video, and it's one reason I reminded everyone how important it was to go back and get their algebra basics, is that there's going to be a trick. Now the reason you know you're going to need a trick is that if you plug 15 in, you end up with that 0 over 0. Remember, the 0 over 0 is an indication that something has to be done to the expression before you can actually plug something in, because 0 over 0 is an indeterminate form. So we know whenever you see that, you've got to back up and do something different. If you in fact did that preliminary video, you'll probably remember that the trick for solving this problem is rationalizing the numerator of that expression. You've got a two-term numerator, and the trick is to multiply the top and the bottom of that expression by the conjugate of the numerator. What is the conjugate? It's what you get by changing the middle sign. So if there's a plus in the middle, you change it to a minus. If there's a minus in the middle, you change it to a plus. So in particular, the trick here is to multiply the numerator and denominator by the conjugate of the numerator. So the numerator had a minus sign, so you have to multiply by a plus sign, and whatever you do to the numerator of a fraction, you have to do the same thing to the denominator so that it's an equivalent fraction. And again, you've seen this before if you did the algebra preliminary video. So what you end up having to do is do the FOIL method on the numerator. You've got first, outer, inner, last. Down bottom, you don't really need to multiply it out. You're focusing on the numerator. Just write the denominator as a product, but don't try to multiply it out. But up top, it's important to multiply it out because the whole idea of using this trick is to get rid of the radical in the numerator. So when you FOIL this out, you get first, outer, inner, last. You get square root of x plus 1 times the square root of x plus 1. You get on the outer term a 4 times the square root of x plus 1. Inner term is minus 4 times the square root of x plus 1. And the last term is minus 4 times 4, which is minus 16. If you continue simplifying that, what you'll see is that the plus here and the minus here add to 0. When you multiply a radical by itself, it's like squaring the radical. So instead of writing it times itself, what you really could write is that it's really squared. And when you square a radical, it just pops the radical off. So you end up with just the expression under the radical, which in this case is x plus 1. Well, now that works out nicely because up top you've got x plus 1 minus 16, which is x minus 15. Well, that's really nice because you've got an x minus 15 factor down bottom. If you cancel them, you end up with 1 over the quantity square root of x plus 1 plus 4. And at this point, there's no reason why you can't just plug the 15 in. And when you do, you get the answer 1/8. Because the square root of 15 plus 1 is square root of 16, which is 4. 4 plus 4 is 8. And again, you saw that calculation without the limit part of it in the preliminary video. And if you haven't done that, that's a really good thing to do because you're going to come across these algebra issues all through the course and you need to deal with any deficiencies you have before it gets way into the course. So this looks like a lot of work, and maybe it is, but it's only occasionally that you have to go to that much trouble. Most of the time you can just plug in. Some of the time you got to do a tiny bit of factoring and then canceling. That's not so bad. And then once in a blue moon you have to work a little harder, like here. Not that often though. Do another example. What if you have the limit of the quantity x squared over the quantity x minus 1? Again, if you try to plug in, you get a 0 in the denominator, but it's not 0 over 0. 0 over 0 tells you that you can simplify something, whether by factoring or by multiplying by the conjugate. Something will cause things to simplify and something will cancel out. 1 over 0 is not that flag. Whenever you get 1 over 0, what that's really telling you is that the limit doesn't exist. 0 over 0 tells you to back up and try to do something that will eventually allow something to cancel out and let you plug in. Anything but 0 over 0 is a flag that says the limit doesn't exist. A lot of times the problems will tell you to write D and E for does not exist. So be careful about watching for those flags. 0 over 0 implies some type of algebraic manipulation that leads to something canceling and eventually plugging in. But anything but 0 over 0 is an indication that the answer is D and E. Now let's look at these things more graphically. I want to go back to the idea of left and right hand limits with a graph like this. It has a left piece, it has a right piece, and it actually has a dot right at x equals 3. So if I'm asking about limits as x approaches 3, I really need to know from which direction. So in this particular problem, I'm asked to find the limit of the function as x approaches 3 from the left. So 3 is right there between 2 and 4. So I'm approaching 3 from the left. Well, if I'm coming from the left, that means that I'm traveling toward that open circle on the segment that's on the left side. So I'm getting closer and closer and closer to that open circle. And as I did that graphical example earlier with the parabola, you can see that as I get closer and closer to 3 from the left, I'm getting closer and closer to that open circle, and that open circle has a y value of 1. So the left-hand limit is 1. You're just traveling down along the left-hand segment, getting closer and closer to the value 3, which takes you to the y value of 1. If you're coming in from the right, though, you're traveling along this segment, but you're getting closer and closer, so you're going this way. Well, what's happening now is you get closer and closer to that open circle from the right. That's what the plus sign means. Then the y value is getting closer and closer to -3. So the left-hand limit is 1, the right-hand limit is -3, and that means if I ask you about the limit without reference to left or right, it will not exist. It has to have an agreement between left and right hand limits for the overall limit to exist. So once you get used to this, this is trivially easy. You need to practice until you think it's trivial. And you have D and E because the left and right hand limits are not equal to each other. We do quite a few exercises throughout the semester with functions like this, functions defined by different rules depending on what the value of x is. You might have something like this. F of x is x plus 1 when x is bigger than 3, and f of x is 4 minus x when x is less than 3. So I want to find the left, right, and overall limits for this problem as x approaches 3. So we'll start off with the limit as x approaches 3 from the left. That means that we're close to 3 but less than 3. Well, less than 3 means we're on the bottom rule. We're on the rule that says you take 4 minus x. So when you're getting close to 3 from the left, you're actually using the function 4 minus x. As x gets close to 3, the y value is just going to be 4 minus 3, which is 1. So once you decide which piece you're traveling in on, that replaces the generic f of x, and you can do the calculation by just plugging the value in. Same thing for the right-hand limit. If I want to take the limit as x approaches 3 from the right, I'm traveling that front. Well, from the right means bigger than 3. So that means I'm traveling on the piece that's defined as x plus 1. So f of x becomes x plus 1, and when I plug 3 in there, I end up with 4. So the left-hand limit is 1, the right-hand limit is 4. Well, if the left-hand limits and the right-hand limits don't agree, we have to say the limit is going to be does not exist. Again, once you get the idea of what's going on here, it's really very simple. I want to end this discussion with some rules for limits. Don't make too much of these because most of them are just common sense, and if I didn't write them down at all, it's probably what you would do anyway. But I do want to document some of these things so when you go back and study later, you'll have something to look at. But there are things, for the most part, that it's the way you would do them even if you didn't have the rule written down explicitly. A lot of formalities here, but basically we've got a function f whose limit is a as x approaches c, and another function g whose limit is b as x approaches c, and that's going to be the setup for the rules we're going to talk about. The first rule just says that the limit of a constant is that constant. So if you're taking the limit of a number, it's just the number. And if you've got a number times a function, you can just hold the number off, take the limit of the function, and then multiply by the number. So the limit of a constant is the constant, and the limit of a constant times the function is just the constant times the limit of the function. And again, I know formalizing these things may seem awkward at best, but I want you to have something you can look back later on when you're studying for the test and just say, oh yes, I remember that. And again, what I said is that it's just saying that the limit of a number is the number, and the limit of a number times a function is just the number times the limit of the function. And for example, if I ask you to find the limit of 18, no matter what x is approaching, the answer is just 18. What x approaches doesn't even matter because there's no x in the expression. The limit of a number is just the number. It's that simple. The limit of 2e to the x as x approaches 0 is just what you get when you plug 0 in for x and you end up multiplying it by 2. That's all it's saying. So you get 2 times e to the 0. E to the 0, anything not 0 raised to the 0 power is 1. So you get 2 times 1, which is 2. And 2 times 1 is 2. Second rule says if you're taking the limit of a sum or a difference of two functions, you can do each one separately and then just add or subtract. Again, it's a common sense thing. It's probably what you would have done anyway. If I told you that the limit of f of x as x approaches 4 is 16 and the limit of g of x as x approaches 4 is 8, and then I ask you to find the limit of the difference of the two functions, all you do is take 16 minus 8. Again, it's what you would do if you didn't even know what to do, which is nice. A third rule, if you're doing multiplication instead of addition or subtraction, again, it's what you thought it would be. If you're taking the limit of a product, it's just the product of the limits. So if I told you that you had the same situation as before, the limit of f of x as x approaches 4 is 16, the limit of g of x as x approaches 4 is 8, and I wanted you to find the limit of the product of f and g, it would just be 16 times 8, which in this case would be 128. It also works with division as long as you're not dividing by 0. So with those same numbers, you would just do 16 divided by 8 would be 2. So these rules are formalizing things so you can look back at them later, but in reality, if you didn't have them, chances are you would do what they say to do anyway because they're kind of natural. Sometimes you get these things where you really need to think about what you're going to do next, but these rules are very intuitive. So they're there for your reference, but in practice you probably don't need them much as you're just working problems. And I'll throw in the one about polynomials that I did earlier. If f is a polynomial, then all you've got to do is plug c in. If you plug the value x is approaching into the function for a polynomial, you get the answer. So you always like dealing with limits involving polynomial functions because all you do is plug in. So if I ask you to find the limit of x squared plus 2x as x approaches 1, all you've got to do is plug 1 in and get an answer of 3. Practice makes perfect on all these, and if you don't practice a lot, you're probably going to regret it later. Practice, practice, practice.